Let's see here. South Pammit Road is here, so Highland should be up a ways. Take a right on the Highland and the lighthouse should be on my left. Okay. Light is all around us. Even when it's cloudy or raining, sunlight reaches the earth. How do we know this? Well, we wouldn't be able to see anything unless the sun or another light source was shining. See, objects on the earth reflect light. The reflection of that light is what allows us to see the objects. This is important to know because it helps us understand not only how we see, but how things that we often take for granted actually work, like this mirror or the video camera that's taping me. What do you think happens to light when it hits a mirror? When light rays strike a mirror, they bounce off the surface or are reflected. The light rays bounce off of the mirror at the same angle at which they hit. If I stand in front of this mirror, my image is reflected straight back. That's why I can see myself. If I stand off to one side, I can't see myself. But if the camera moves to the other side, hello, it can see me because of the same principle. The light is reflecting off the mirror at the same angle that it's hitting the mirror. Television stations use a mirror on a piece of equipment called a teleprompter. A computer image of the script is reflected off of a special mirror placed in front of the camera lens. The mirror lets the camera see through it from one direction, but reflects the script from the other direction. In this way, the person reading the news can follow the script while looking directly at the camera and you. You didn't think they memorized all that stuff, did you? Even the president uses a teleprompter. It's much more sophisticated than the kind in a TV studio, but it works on the same principle. The speech is actually reflected on these see-through stands, so he can appear to look out into the audience while reading the speech. Curved mirrors produce different results than flat mirrors. There are two types of curved mirrors: convex mirrors and concave mirrors. The surface of a concave mirror is curved inward. Concave mirrors converge or bring together light. Objects that are up close to the mirror look larger. This flashlight also has a concave mirror inside it. The bulb is placed very close to the mirror, and because of the mirror's concave shape, the light is reflected to produce a concentrated beam of light. The surface of a convex mirror is curved outward. Convex mirrors diverge or spread out light. Have you ever seen this message? When you look into a convex mirror, objects look smaller and farther away. A convex mirror provides a larger viewing area than a flat mirror does, but the images are closer than they look. Convex mirrors are generally used to increase visibility for safety and security reasons. Store owners use them to watch for shoplifters. Trucks and other vehicles use them to increase the driver's range of vision when driving. Reflection also helps us drive safely at night. Some road signs are coated with tiny beads of glass that reflect light from a car's headlights to make them look bright at night. Here are some other things to reflect on. Why is it that you can see your reflection in objects other than mirrors? Why is your image sometimes distorted when you see your reflection on the side of a toaster or other shiny object? What kinds of mirrors are used in amusement parks to distort the size and shape of your body? How do you think they work? Cape Cod light. Maybe this will help. Huh. The first lighthouse on Cape Cod was built here in 1798. Light travels in a straight line and at a constant speed when it travels through the same material. However, light travels at different speeds in different transparent materials, such as air, glass, or water. So, when light travels from one material to another, like from air to glass, its speed changes. It travels more slowly in glass than it does in air. As a result of this change in speed, light bends as it travels from one material to the other. This bending of light is called refraction. Lenses are specially shaped pieces of glass or plastic which are designed to take advantage of refraction. Lenses have curved surfaces so that as the light passes through the lens, it is refracted. Depending on their shape, lenses can be used in different ways. There are two types of lenses, concave and convex. The surface of a concave lens is curved inward. The surface of a convex lens is curved outward. This magnifying glass is an example of a convex lens. When light passes through a convex lens, it converges or comes together. Convex lenses are used to magnify the size of images. You'll find them in binoculars, telescopes, and microscopes. The lens in each of your eyes is another example of a convex lens. The light, reflected from an object, enters the eye through an opening called the pupil. The colored area, called the iris, is a muscle which controls the amount of light coming in. When light passes through the lens, it is refracted and projected on the retina, the inner surface of the eye. The lens of the eye changes shape in order to focus on objects at distances near and far. If the focused image does not fall directly on the retina, it will look blurry. In this case, the eyeball is too long, so the focused image is falling in front of the retina. This is known as nearsightedness. Eyeglasses with concave lenses which diverge or spread out light will bring the focused image back so that it falls on the retina. If the eyeball is too short, the focused image falls behind the retina. This is called farsightedness. Remember how I needed to use glasses to read that information about the lighthouse? I'm farsighted, so I have to use corrective lenses, either glasses or contact lenses, to read things up close. Eyeglasses with convex lenses, which converge or bring together light, will bring the focused image forward so that it falls on the retina. Did you know that as far back as the 13th century, people wore glasses containing convex lenses? And the first contact lenses were made in 1887. They were made of glass and were worn directly on the eye. Records show that they were large, thick, and not very comfortable. Here are some other questions to think about. Why do plants growing out of a pond or a spoon in a glass of water sometimes look bent? What kinds of lenses do you use occasionally or every day? Are plastic lenses better than glass lenses for eyeglasses? What are the advantages and disadvantages of each? Like the eye, a camera works by allowing light to enter through a lens, or a series of lenses. The difference is that a camera, like this one, records the image on film. Scientists and engineers used their knowledge of lenses and mirrors to help design this camera. Unlike the eye, cameras use a group of lenses, one of which moves back and forth to focus the image on the film. More than one lens is needed because a glass lens can't change its size like the lens of your eye can. The mirrors inside the camera allow the photographer to see through the lens exactly what the film will record when the photograph is taken. When this button is pressed, the mirror flips up so that the image can be captured on film. Lenses and mirrors were also used in the design of this lighthouse. In the early days of shipping, people built fires on land and kept them burning through the night so that passing ships would know how close they were to the coast and the dangerous shallow waters. Eventually, the open fires were replaced by oil lamps on towers. At first, mirrors were used to direct the light, similar to the way flashlights work. Then, in 1822, Augustin Fresnel designed a lens made of highly polished glass prisms set in a concentric ring-shaped arrangement. Through a combination of reflection and refraction, the beam of light could be projected over greater distances. Today, most lighthouses are automated. This one, the Highland Light on Cape Cod, Massachusetts, is powered by electricity and uses a mirror to direct the light. On a clear night, its light can reach distances of 24 miles. In 1609, the Italian astronomer Galileo knew that there were worlds beyond our own, even though they couldn't be seen with the naked eye. He designed a telescope to view the sky at night. A refracting telescope, like the one Galileo used, consists of two convex lenses, one on each end of a long tube. The lens closest to the sky is called the objective lens. It gathers the light and focuses it to form an image. The other lens, called the eyepiece lens, magnifies that image so you can see it with your eye or record it with a camera. Remember, lenses refract light. That's why this type of telescope is called a refracting telescope. The Yerkes Observatory in Wisconsin contains the world's largest refracting telescope. The lens is about 1 meter in diameter. In 1668, Isaac Newton designed another type of telescope. His was called a reflecting telescope because it used mirrors to reflect light. A reflecting telescope uses a concave mirror. When light enters the open end of the telescope, the concave mirror reflects light to a flat mirror, and the image is reflected out to the eye or a camera. The Hale telescope on Mount Palomar in California is one of the world's largest reflecting telescopes. Its mirror is about 5 meters in diameter. The Hubble telescope is also a reflecting telescope. It operates in space and is able to see objects that telescopes on Earth can't see because light from distant objects is distorted as it passes through the Earth's atmosphere. So, telescopes help us to observe distant objects. But what about objects that are closer but too small to see, or objects that we want to look at in more detail? In the late 1600s, Anton von Leeuwenhoek invented a simple microscope. Simple because it had only one convex lens. He could magnify objects as much as 250 times their size. At around the same time, Robert Hooke used a compound microscope. His microscope contained two convex lenses connected by a tube. For centuries, lenses and mirrors have provided us with a unique view of the world, a view that our eyes alone cannot provide. From simple flat mirrors that reflect our own image, to curved mirrors used in flashlights and reflecting telescopes, to lenses that allow us to examine distant galaxies or microscopic organisms. Our understanding of the world around us would be far more limited if it were not for lenses and mirrors. Here are some questions to think about. What devices around your home or school use a combination of lenses and mirrors? Can you think of anyone who uses microscopes or telescopes in their work? What about just for fun? Can you design a device that would use lenses and mirrors together?